Hello students. Our next example is conical pendulum. So here is a mass m fixed through a length string with the length L, which is massless. Is tied to the end of a hub that rotates with a constant angular frequency omega. This is rotating with an angular frequency omega. So the mass will be rotating around this circular path with an angular frequency omega. And this string is at an angle alpha with the vertical. So this is a problem. Mass m is fixed at the end of a rod of length L and negligible mass that is pivoted to swing from the end of a hub that rotates at constant angular frequency omega. Okay, the mass moving with steady speed in a circular path of constant radius. So this mass is moving with a steady speed in a circular path of constant radius. The problem or question is to find alpha and the angle the rod makes with the vertical. So we have to find out the relation between alpha and the angular frequency of rotation. Now we start with the force diagram equation. Here is the mass m. It has one force which is the weight towards downward direction and a tension with which the rod pulls the mass, and W is the weight of the wind. These are the two forces acting on the mass m. You can see this angle is also alpha, and this is the radial direction, and this is the y direction. So W is acting in the y direction. Now we resolve the T into two components. So here you get a vertical component along the y direction as T cos alpha, which is exactly opposite to W, and you get a horizontal component along this direction as T sin theta. These are the two components of T. So the vertical equation is, so what is the vertical equation? T cos alpha. Here it is the T cos alpha minus W. Both are opposite to each other. So T cos alpha minus W is equal to 0. This is the vertical equation of motion. Why it is 0 means there is no motion along the vertical direction, or along y direction there is no motion for the mass. Okay, so that is why right hand side it is 0. Now to find the horizontal equation of motion, note that the bob is accelerating in the r direction at a rate AR is equal to minus omega square r. This is the radial acceleration. AR is equal to minus omega square r. R is the radius of the circle and omega is the angular frequency with which it is rotating. Okay, then so what will be the left hand side? The force value, that will be T sin theta opposite to R. Okay, of R is towards outward direction, and you have T sin theta towards negative R direction. So the equation becomes minus T sin theta is equal to M into A. A is AR, or the radial acceleration. So minus M R omega square. This is the horizontal equation of motion for the bob. So this is the vertical equation of motion, and this is the horizontal equation of motion. Now we can see from the figure that R is equal to L sin alpha. So we have T sin alpha is equal to, substitute R as L sin alpha, you get M L omega square sin alpha. From this relation we can cancel sin alpha throughout this equation, which gives T is equal to T, the string force or the tension, is equal to ML omega square. This is equation number 4. Okay, combining our equation for the vertical equation 1 and 3, this equation we get, substituting for T, you get ML omega square cos alpha is equal to W. This is our relation. Since W is equal to mg, the weight of the body, that is equal to mg, when we substitute mg, m get cancelled. We get the equation from 5. Equation 5, we can write it as cos alpha is equal to g by L omega square. This is our relation to be found out. It is a relation between alpha, the angle with which the string is extended from the vertical, and the angular frequency omega with which it is rotating. We have to analyze this equation more detail. Okay, this is our relation connecting alpha and omega. Okay. Now, when omega becomes, since it is in the denominator, when omega tends to infinity, cos alpha is equal to 0, or that means alpha is equal to pi by 2. That means it is almost horizontal. The rotation is almost horizontal. This is reasonable because at high speeds we expect the bob to fly outward, which is equivalent to expecting that alpha tends to pi by 2. So this is a possible solution. However, at lower speeds, the solution becomes unreasonable. That is, as when omega tends to 0, our solution predicts cos alpha tends to infinity, which is a non-possible value for cos alpha. Its range is from -1 to +1. So this is an impossible solution. So where have we done something wrong in the calculation? We have to look into that region. So we have to analyze that equation more when we substitute for this condition, when omega is equal to root g by n, this is the equation for the angular frequency for a pendulum, the normal simple pendulum. You get cos alpha equal to 1 and sin alpha is equal to 0 for this case. So in this case, when cos alpha equal to 1 and sin alpha is equal to 0, that means alpha is equal to 0 case. The bob is simply hanging vertically. There is no oscillates or there is no motion for the bob, right, in this condition. Now in going from equation 2 to 3, we have divided equation 2 by sin alpha. Okay, you can see in the derivation that was a serious error which has we divide it by 0. In this case sin alpha is 0. We cannot divide that equation by a 0, which is not permissible. That was the mistake we had made in that step. And second, another possibility is that sin alpha is equal to 0 when t is equal to w. This is a possible solution. This solution is true for all values omega. In this solution, we can find that when t is equal to w means the bob hangs straight down. There is no angular slanting for the string. So the bob simply hangs straight down. So you can see a relation or a plot connecting cos alpha and omega. And then, so this is the graph connecting cos alpha and omega. We have drawn a curve like this for cos alpha is equal to g by L omega square. This dotted line in the graph shows a inconsistent region. This is the inconsistent region, and below this only there is a stable variation of the pendulum occurs. Okay. So this is the critical point where omega is equal to root g by L. Physically, for omega less than or equal to root g by L, below this region, the only acceptable solution is alpha equal to 0 or cos alpha equal to 1. This is the only acceptable region. So this is the critical point. You can say like that. And this is the only acceptable solution for this condition. Now for omega, when it is greater than root g by L, there are two possible solutions. One is cos alpha equal to 1 and cos alpha equal to g by L omega square. This is a regular relation. The first solution corresponds to that the bob is spinning rapidly but hanging vertically. Bob is spinning rapidly but hanging vertically. There is no pendular motion occurring. And this is our general solution where the bob flying around at an angle alpha with the vertical. These are the two possible solutions for omega greater than root g by L. And when omega is less than or equal to root g by L, the only acceptable solution is alpha is equal to 0 or cos alpha equal to 1. Below this region, this dotted line region, it is not mathematically inconsistent region, okay, or the unstable region. This is how we analyze the problem of conical pendulum.